Hello and welcome back to another episode of Mr. Walker's Chemistry. Today we're going to be talking about the history of the atom. Where did the idea originate and how far has it progressed? Okay, so we'll start way back in ancient Greece. This guy named Democritus, around 400 BC, he proposed the idea of an atom. He proposed that everything he saw was made up of really, really tiny, indivisible parts, which he called atoms, which comes from the Greek word atomos, which just means not cuttable or indivisible. He said that once you got to these little tiny building blocks, per se, that you just can't see with the naked eye, that you could no longer split them in half. All right. In other words, these were finitely small, and he was clearly wrong. All right, we know much more about this now, and we haven't even found the smallest thing yet in physics, and physicists are still trying to figure out what is the smallest, how small can we go. So we're going to jump several hundred years here, and there wasn't really a modification to the idea of Democritus until 1803 with Mr. John Dalton. He developed Dalton's atomic theory, named after himself, of course, and he said that something very, very similar to what Democritus said. He made one minor contribution which led to a big change and a big revolution in what we think of as terms of the atom. All right. While he still said that everything is made up of these tiny indivisible particles called atoms, and that they can't be broken down He said that they can be broken down further, and just that the properties will not be retained. So he said that all atoms of the same element, for example, carbon, something that was well known about at the time, is exactly like all atoms of carbon are the same, and all atoms of oxygen, of iron, of all these other things that they knew about at the time were the same. But once you broke them down into the smaller parts, they could no longer be identified. They just became these generic sort of things. So this is talked about in the proton video a little bit, where protons, neutrons, electrons, that introduction to the atom, they're all, a proton or neutron, electron, compared to another proton, neutron, electron, or, proton is a proton, proton is a proton, no matter whether it's in oxygen, carbon, etc. All right, so this was John Dalton, 1803. Minor revision, just said that we can break them down, but the properties are lost. So his idea of an atom is this, okay? A sphere. There was nothing, unique about it or different or anything. Everything was just spheres, and you just had different types of spheres that made up everything. He did say that atoms could not be created or destroyed, which he was correct there. Matter cannot be created or destroyed. It's the law of conservation of matter. So he was correct in this. He'd also made another significant contribution directly to chemistry, saying that if I take different types of atoms and I rearrange them, I get something else. I haven't destroyed the atoms, they're just rearranged. It's like saying I've got a Lego house, and now I'm going to take all the Legos and break them down and build a bridge out of the same Legos. And that's kind of what it was. And he was almost right there. Later on in the 1800s, about 30 years later, we have a minor contribution which led to big discoveries from Michael Faraday. Michael Faraday was a physicist. He really didn't have a whole lot of interest in chemistry. But he found that they were related because atoms can possess an electrical charge. Today we call these ions. But at the time he was just more looking into how can I make electricity? How can I make it better? And he said, well, I found that these atoms contain an electrical charge, so maybe we can use that. Now we come to one of the most important and significant figures in the development of the current model of the atom. All right, Mr. Thomson, in 1897, took part of Dalton's theory, took Faraday's discovery, and he put them together. He said, okay, well, Dalton said that atoms make up everything and you can rearrange them to make other things. Faraday said they have charge, but didn't know where the charge came from. So Thomson said, well, let me figure this thing out. How can a sphere have that makes up everything have a charge? Where does that charge come from? So he discovered the electron. Okay, you should know this. All right, J.J. Thomson discovered the electron using a cathode ray tube. I've got more information on that on the next slide here. All right, so the cathode ray tube is fairly simple. I'll demonstrate this in class for you. But you have a positive end called a cathode and a negative end called an anode. This is in a vacuum, so there's no other matter for the stuff inside the electrical charge to interact with. This is not like lightning per se. Okay, lightning interacts with the air and everything, and you get the boom and all that sort of stuff. All right, this is just running an electrical charge through a vacuum and looking at what you can see. So he did that. He ran an electrical charge through a vacuum, and he saw this green beam, and he didn't know what the green beam was made of. He didn't know how it got there. So he decided to figure it out. So if you put a magnet, all right, let's say we put a positive end of a magnet right here. If these are negative, they should be attracted to the positive. So they should start to bend up towards that. And if you put a negative on the other end, they should bend away from it. So I'll demonstrate this in class, and we'll see if that does in fact happen, which it should if J.J. Thomson was correct. Okay, so going back here, he did discover that they have a negative charge, and he called them electrons because of electricity, and he created this plum pudding model. Now, plum pudding hasn't been around for a long time, so you may not know what plum pudding is. Plum pudding is like any old pudding, except that you keep whole plum pits in it. All right, so you mash up all the pits, the plums, to make the pudding, but you leave the pits in there. So he said that the plum pits were the electrons, and the mushed up flesh of the plum was the positive stuff. And so these positives and negatives held each other together. So you can start to see where we're getting towards the modern atom, where you've got protons and electrons holding each other together. Doesn't look quite like this, but we've got a little ways to go. This is just at the turn of the last century. Okay, so we're going to go on to this man, Robert Millikan, in 1909. While J.J. Thomson discovered the electron, he didn't fully understand the charge. He hypothesized that it was negative because of the cathode ray experiment, but he didn't know the charge exactly, and he didn't know the mass exactly of these particles. He had just seen them. So Robert Millikan designed this really ingenious experiment called the oil drop experiment. And keep in mind, this is before the days of electron microscopes and computers and things. This was just a man with a basic microscope, light microscope, some oil, kind of one of those old perfume spray bottle type of things that would create a vapor of oil. And he knew that oil droplets fell with gravity. Now, a long, long time ago, Newton figured out how fast gravity pulls things down, the whole apple on the head thing. So Millikan just used that information from physics to figure out how fast these things dropped through an opening. He also had charged plates, positives and negatives. And using these, he could figure out the exact charge of an electron. Okay? If I have a negative plate at the bottom and a positive plate at the top, opposites attract. So by putting a positive charge on the top, these oil drops, which are negatively charged, try and get to the positive, and they are repelled by the negative. So I put a very strong positive on here, these will appear to float in place. They will balance out. And that's what he was looking for. He's like, where can I make these oil droplets kind of float in place? And then I'll know the exact charge that I need because I'll have that charge on the positive and negative plates. And he was extremely accurate, and today's measurements are still very comparable to what Millikan found. You don't need to know this, though. It was just kind of an interesting, neat fact of what we know and how we know it. So the next big advancement in the model of the atom came with Ernest Rutherford in 1911. All right, just about 20 years after J.J. Thomson's plum pudding model. And he did the gold foil experiment. Okay. The gold foil experiment is extremely famous in chemistry because it proved Thomson wrong. And that's a big deal. Okay. So let's examine this gold foil experiment for a second. All right. So essentially what it was is you have this source of alpha particles. Alpha particles are the nucleus, only the nucleus of a helium atom. 2 protons and 2 neutrons. That's it. Then he had a very, very, very thin sheet of gold foil. The foil was only 1 atom wide. It's very thin, okay? So it was 1 atom thick, and he fired these alpha particles at the gold. And he observed what you see here, that some particles went straight through the gold and didn't hit anything, whereas others were deflected. And this was very odd to Rutherford, because he actually initially was trying to prove Thomson correct. So let's pull up the 2 models here. So on the top, we have Thomson's plum pudding model. And in theory, these lines represent the path that Rutherford hypothesized the alpha particles would take. He said if it really is plum pudding, there should be nothing heavy enough or dense enough inside the pudding to deflect the alpha particles. They should just go right through, like bullets through jello. Okay? But what in fact he found was that they were deflected, which means there was something somewhere in the atom that was big enough and dense enough to deflect an alpha particle. So he said, well, most likely it's in the middle, and it's very dense, so it has a lot of mass in a small area, and that's what's causing my alpha particles to deflect. So you can see some of the lines, they go straight through, like what you see here in this experiment, and some are bounced off and hit the deflector in other areas. All right. So this radically changed the model of the atom. We went from the plum pudding model of Thomson to starting to get to the modern atomic model, modern atomic theory that we see today, where you've got a nucleus in the middle and electrons around it. So let's keep going here. Niels Bohr, 3 years after Rutherford's gold foil experiment, found out some very interesting information. He said, okay, I'm observing hydrogen, and if I heat hydrogen, it will give off light, and I can heat it more, and it will give off a different color light, and so on and so forth. So he looked at these things. He said, okay, I can quantize this information. In other words, I can figure it out mathematically. So he developed what we call the quantum mechanical model. And let me show you what that is. All right. Oh, sorry. I'm going to go, we'll stay here for a second. The quantum mechanical model says that the electrons go around a nucleus. So if I have a nucleus, and then I'm going to have these orbits around it, and the electrons are on the orbit. In a way, he combined Thomson. He figured out how electrons fit into the whole model. Rutherford figured out how the nucleus fit in, and Bohr figured out how the electrons play a role. Okay. Now, electrons are a little bit weird, though. Okay, we're going to talk a lot about electrons. They are very weird. So here's just a very brief video. I hope it works here.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
Okay, so by going quantum, they mean really, really tiny, basically the atom.
Electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of...
Okay, so that video was just to demonstrate how weird this model really starts to get. You know, with Bohr's model, it's pretty simple. A nucleus with things, you know, with orbits, what he called orbits around it. Well, once this discovery that this man in the video was talking about was made, we started to get into this really weird world of quantum mechanics that Erwin Schrödinger had to revise the atom as a result. So based on the research shown in the video, Schrödinger figured out that electrons do not travel in orbits, but rather move around randomly, like waves, which he called clouds. So he updated the quantum mechanical model, meaning the small moving model, and it's sometimes called the electron cloud model. So if I pull up this diagram here, this is what Schrödinger envisioned. Okay, you've still got a nucleus in the middle containing protons and neutrons, but the electrons are more scattered throughout. Okay, they're not following perfect little rings. It's more like anywhere in here that's shaded you can have electrons, and they're constantly moving, and it's really hard to tell where they are. So the final thought on the history of the atom is that no model is perfect. We're still revising what we know about the atom to this day. And if you go into chemistry or physics, you're going to learn a lot about all sorts of really weird things like up quarks and down quarks and bosons and really strange things that dictate more of how protons, neutrons, and electrons work, but we still don't fully understand. And it's really hard for me to come up with an analogy for what an atom is, because the only thing that behaves like an atom is an atom. The solar system model, it works well when you're talking about Bohr's model because of the orbits, but because that model is outdated and not correct, we're talking about the electron cloud model, it's really, really hard to think about. So review key points, all right? Things that you should know. People have always wondered, how small can we go? Starting back with Democritus, and he was wrong, but he still said, I bet we can go to this little tiny building block. Well, we can still go to a really tiny building block, but how small does it go? Because we're still splitting open things to find smaller and smaller and smaller gifts inside the packages. All right. Big names you should know. Democritus, you should know Democritus. First guy to suggest atoms, smallest. You should know Dalton. Okay, Dalton proposed that everything was tiny, but that they had different properties depending on other things. Okay, Thomson, know the plum pudding model. All right, plum pudding model, electrons and protons only. He did not know about neutrons at the time. All right, so Democritus, Dalton, Thomson with the plum pudding. Rutherford, you should know the gold foil experiment. All right, we're going to do some things in class with this so that you remember the gold foil experiment. This disproved Mr. Thomson, and he proved that there was a nucleus, so no pudding. Rutherford said there was no pudding. Bohr expanded on this and showed that you have protons in the middle with electrons orbiting them, and he developed this based on his experiments with hydrogen. Finally, Schrödinger developed the quantum mechanical or electron cloud model, in which the electrons don't actually orbit, but just move around randomly in these wave-like patterns, similar to air in a balloon or bees around a hive, something that seems very chaotic, and scientists still don't fully understand how it all works, as you saw in the little flash video. Okay, I've got a really neat demonstration in class to show, how observing something can change its state. They are really neat. They'll kind of blow your mind. And I think it's a good way to start off with the atom and showing, how weird things are going to get for you guys. And it should be a lot of fun for us throughout the year. Okay? So please review these things. Democritus, Dalton, Thomson, Rutherford, Bohr, and then Schrödinger with the electron cloud model. I hope you learned something, and I'll see you next time.